Hello, Calculus 1 fans. Going to talk about optimization. I think it's currently section 4.7 in our Math 124 course. I'm going to talk about thought process. I'm trying to finish up. I've made reviews for most of the other topics of the course, and I know our students this term are gearing up for final exams. So I want to talk about optimization, and then I'll make a separate one about curve sketching. I really enjoy optimization. It's one of the big reasons, one of the big places we use calculus. I actually think these questions in a lot of ways are easier than other ones on the exam simply because you have a clear process and goal. And so I want to explain that piece. I have a bunch of questions prepared here from old exams. I'm not going to work all the way through every one. I'm going to talk about the structure of your solution, which I think everyone can know immediately when they read a question. And I want to explain what I mean by that. Okay, so a few notes and then we'll launch into the questions. Ultimately, in calculus, you've learned how to take any function whatsoever and take its derivative. How is that useful? This is just a quick recap. Well, if you're trying to study the height of something, its derivative is the slope. So I always tell students, you definitely should know that piece. And you should also know that if you were looking at a graph, if you could actually see it, and you wanted to know when it was biggest, you'd want to know where these bumps are. Now you've learned to call those by official names, critical points. You'd also like to know where the endpoints are. So in our mind's eye, we're always thinking about, if I want to study something, if I want to study the height of something, I really want to know what the formula for the slope is, and I'd like to know when the slope is 0. So that's an overarching theme throughout the term. Okay. And then from that, we got to make the correct conclusions. There's other stuff. So that brings a central goal to a question about optimization. An optimization question is asking you, or asking you about some function. And in order to answer when it's biggest or smallest, you're going to need that function. You're going to need to take the derivative. And you're going to need to find when the derivative is 0. Of course, you still have to make correct conclusions. So that is our number one goal, our guiding light in these problems, is to find a one variable function for the thing we want to optimize. Now, if you move on to calculus 3, you'll talk about how sometimes you can solve it when there's 2 variables or more, but everything in calculus 1 will boil down to a one variable function. Okay. Once we find that one variable function, we're going to take its derivative, set it equal to 0, and make appropriate conclusions. To me, there's just one thing. There's really just one question. What do we want? What are we optimizing? In math, we call that the objective. The moment I write down the objective, I almost always know what to do in these problems. And that's actually really easy to identify. The objective is the thing you're optimizing. So I have a question right here you can already see from an old final. I just grabbed a large collection of them. And it's usually right at the end or at the question. You don't even have to read the rest to know how the entire question is going to go. Now, there are details we'll have to fill in, but we're minimizing the amount of material. That is our objective. And it's talking about some cylindrical can, so that is talking about surface area when I read that. So our objective is surface area. I'll just abbreviate it, SA for now. And now you know how the entire problem is going to go. The entire problem we're going to have to probably draw and label, get variables introduced. Yes, there's some stuff to do, but after a bit of work, we'll have a one variable function, and then we'll engage our calculus muscles. We'll take the derivative, we'll set it equal to 0. So I tell students, the moment you read the question, you know the only thing you're going to take the derivative of in this problem is surface area. If you're taking the derivative of something else, you don't understand the idea. Okay, so before I go a few steps further into that particular problem, I thought I would show you a couple resources. So here's my website, my Math 124 website. I have a few things here. So this is if you want to dig into the details more. There's a couple points you might want to think about. So if you want a step-by-step, we're always going to want to visualize. But to me, the visualizing is part of this process of realizing what was given, because you're not going to be able to think about what you're given and what you want. So here I say, what do we want? What to optimize, but that's what we want. The other things we're doing are just going to help us. Like, is there a domain? Is there an end? We know that the ends might be important. And we're going to find the critical numbers, and then we're going to make appropriate conclusions. Now, in our Calculus 1 course, we require a rather precise justification. So because of that, I have this longer section about how can we be sure. One way we can be sure is you can check the endpoints, check the critical numbers, plug each one in and see who wins. Another way is you could do the second derivative test and see if it's a local minimum, and if it's the only critical point, then it's also a global minimum. You could do the first derivative test, do the same thing. So you have a few options. Beyond that, we still need to know the same things you've been using all term, your areas, your volumes. A good place for that, I usually don't hand that out again because I hand it out as part of my related rates section. So in my related rates, I have this here, basically the tools we use. Okay. The other thing I have is kind of some fun questions. There's a homework question, an old final question. I have a collection of classic problems here, which are kind of interesting to think about. All right, so let's get rid of that and just glance at these questions. Again, I'm not going to fill in every detail. That's not what this is for. Students should be able to start these questions. Okay, so we're going to play the game. I have never looked at these questions before. I intentionally started this video without preparing, which probably means I'm going to make some mistakes. But I want you to see the thought process. So when I see this, I go, even before I draw it, I go, my goal is surface area. My goal is to find a one variable function for surface area. Nothing is going to distract that from me. It's my guiding light, my guiding principle here. So that's what I'm optimizing. And the way I find when something's minimum is I take its derivative, say, okay, that's the game I know I'm going to play. So that's what I want. I actually think of almost all math questions this way. Most of the time when people are confused, it's either because they don't know what they're given or they don't know what they want. Now in optimization, we have special names for those. What we want is our objective, and what we're given is the constraints. Since optimization is such a huge area of mathematics, it gets its own words. All right. So now let's draw some pictures. What is this? A cylindrical can. So to me, it would make sense to draw a cylindrical can. And it holds 1.5 liters of liquid. So I'll have to make sense of what that means. So they gave me this 1.5 liters. That sounds like a volume of some sort. So I think I will label that V. I don't know. You really can't over-label. I'm just trying to get to a point so that I can find a one variable function for surface area. Determine the dimensions of the can, base, radius, and height. Okay, so they're making suggestions for things I might want to label. How about radius and height? We'll minimize the amount of material used in the construction. Remember that 1 liter is 1,000 cubic centimeters. Oh, I see. So they're trying to help us get it all in terms of centimeters. So let's rewrite this. So I've decided I'm going to label R, I'm going to label H, and I'm going to label V. Now, none of those are the ultimate thing I want. And that's why it's so important that I already recognize, because what students do is they start taking derivatives of R or H or V. The only thing we're going to take the derivative of is surface area. So a good place to we could even start, but I'll put this here. I feel like I want to write 1,500 cubic centimeters. I did a little unit conversion here because they told me the unit conversion. So again, we could spend a lot of time in the weeds here, but let's just go. Okay, so sometimes students go, well, I don't know the surface area of the can. I assume there's a top and a bottom. I would add a few more words if I was doing this problem. But let's say we assume there's a top and a bottom. If I was there taking the test, I'd raise my hand and say, is there a top and bottom? The area on top is pi r squared. The area on bottom is pi r squared. The surface area you can remember by the next time you go to the restroom, because if you take a piece of toilet paper one time around and unroll it, it's a rectangle. And the area of that rectangle is height times however far it is around the edge, which is circumference. That's how I remember it. Every time I see a toilet paper roll, I remember the surface area of a cylinder. So the surface area altogether is 2 pi RH plus 2 pi r squared. And this is the outer edge of it, and this is the top and the bottom. I'm going to read it one more time, make sure I didn't miss anything. Imagine each cylindrical can. So again, I assume that means top and bottom. That will hold 1.5 liters. Okay, that's my constraint. Determine the dimensions of the can that will minimize the material used. So right away, you see the problem. Our guiding light is that we want a one variable function for surface area, and we currently have a two variable function for surface area. Not only that, if there was no constraint, the question never makes sense. Just don't make the can. Make this 0 and make that 0, and the answer is 0. So without a constraint, the question's easy. But there is a constraint. We have to get it in there. Okay, so next step. What's the volume? Oh, the volume's the area of the base times the height. So you would have to remember that, but you're not going to take the derivative of that. All of this is towards your guiding principle. So when I look at this, I go, which variable would be easier to get rid of? To me, it looks like H would be easier to get rid of. So I have 1500 over pi r squared. And then we have it. The only variable is going to be r. I'm going to plug this in here. And that will give me a one variable function. And then I'm ready to go. So here we go. F of r. If I was doing this myself, I'd probably simplify it as I went, but I'll do it right here. Pi r squared plus 2 pi r squared. And then let's write this the way a calculus student would write it. 3,000 over r, or how about r to the minus 1, plus 2 pi r squared. And now I know how the rest of the problem is going to go. I'm going to take the derivative, I'm going to set it equal to 0, and I'll have to make appropriate conclusions. Now I'm suspecting I'll only have one critical point, but that changes. The problem now just shifts to our standard calculus skills we've been practicing. You might say, well, I don't know those. But this particular one, we're going to hit on this algebra issue, which is how do we solve with negative exponents. I often tell students to return to becoming an algebra student. And often an algebra student would rather not have negative exponents. And then I always say, if you're unclear about how to solve something because there's a fraction, clear the denominators. Is that the only way to do the next step? No. But I'd multiply everything by x squared, and then it's much more clear how to solve. Okay, I'm going to stop for that one and move on to the next one. All right, so I've got several more, and we're just going to ask, what are we trying to optimize? What do we want? Okay, so here's a random other one. I'm going to pull it up here. Okay. You are designing. I noticed there's quite a few cylindrical containers in the older exams. I don't know why. It's not that we really don't ask those that much, but there's several in a row on the oldest exams in the archive. You're designing a cylindrical container of volume this. The top and the bottom must be made of a material costing $3. Okay, too much stuff to read. Let's just go to the end. What are the dimensions that make the cheapest container? That's my guiding light. Don't try to guess anything else. Just now write down what that is. Cheapest means we want the minimum cost. That's our guiding principle. The very first thing we're going to write is cost. The goal is to get a one variable function for cost, take its derivative, and we'll be done. This is where students get mixed up, but they're like, I don't know how to deal with cost. Okay, so now we're going to think about what we're given. What are the constraints? The constraints are that the volume, this is very similar to the last one. The volume has to be 75 pi. The top and the bottom must be made of a material costing $3 per square foot. Surprisingly, this is what bothers students. Maybe it's because you've never had to buy something at a hardware store. I'm not saying everyone hasn't, but if you go to a hardware store and it's $3 per square foot and you buy 10 square feet of the material, it costs you $30. How do I know that? Well, because that's what that means. $3 per square foot. So the cost is going to be 3 times the square feet of what? The top and the bottom must be made, okay, times the area of the top and the bottom. And in my experience, that's the part that really scares people. How do I know that? Because $3 per square foot means 3 times however many square feet of that material you're using. And that's talking about the top and bottom. Okay, plus, while the sides are made of a more expensive material that is 10 times the area of the sides. So I think I'm well past when I should have drawn something. You can definitely draw things right away, but this is what tells you how to do the problem. So this is R, this is H, the top and bottom, so 2 pi r squared. They were nice enough to tell us what this was again, but we know because we can look at a piece of toilet paper. And this boils down to almost the exact same problem we just did, pi r squared h. And by studying several of these, you would say, okay, I'm going to add the formula to my note sheet for surface area. So you would also have this. Substitute this in. I'm going to get a one variable function for r. This is going to be 6 pi. And, oh, does this come out as nice as the other one? Okay, I see. R plus 20 pi. Again, I might make a mistake because I'm not checking things like I normally would. I'm not going all the way through. One nice thing about these problems is that at the end, you can check if your answer is reasonable. You can plug it in. You could try a few other values to see if your answer makes sense as a minimum. So there are a few things you can do. Okay, so hope this is helping. Let's keep going. So I'm going to get rid of that one and do another one. Maybe what I'm going to do, apologies, I'm going to delete some of this stuff. And let's move our way up here. Sorry. Here we go. Let's grab this one. Ooh, a tennis ball. Again, I've never looked at these questions before. Just going to do thought process. So suppose you're standing at a beach on the edge of a water. I looked at them when I did a screenshot of them 5 minutes ago. As you looked westward into the ocean, you throw a tennis ball out into the water. The ball lands 20 meters north and 13 meters west of where you stand. So we must be standing here, but let me keep reading to make sure. The ball, okay. The dog swims at 5 meters per second, but runs 13. Okay, there's lots of information, overwhelming amount of information. And so that's why it's good. We have this plan of what do we want? What are we optimizing? Minimize time. It's not hidden. Minimize time. And so you know the very first thing you're going to do is write time. And you know that your guiding principle for the whole problem is to write a one variable function for the time it's going to take the dog to get there. And that will tell me everything I need to know. You might say, well, I don't remember how to get time, but you certainly will have done those sorts of questions on the homework. I mean, I always can remember that speed is distance over time because I've driven a car before and had to think about I'm going a long ways, how long is it going to take me? So if you rearrange, time is distance over speed. And you've probably experienced that before. And you could always run an experiment. You could say, if I go 60 miles and I'm going 30 miles an hour, oh yeah, it's 2 hours. I do distance over speed. So you're not stuck just remembering formulas. You can also use what you know from your life and run little experiments. Okay, so in my mind, I'm probably going to do distance over speed. Okay, so now let's go back to the question and do some labeling with a goal of finding a one variable function for time. So you can see how I have no worries about problems like this. I'm always happy to do problems like this. It feels like I'm actually doing something. Don't let a problem like this scare you on the test. You're going to have lots of stuff you can do. Okay, the ball landed 20 meters north and 13 meters west. So they're telling me a few things here. 20 and 13. That's what I see. Now, the one problem I have with this is once the ball lands, it's probably going to float in and out, but I assume that's not what we're saying. I guess this should be a pond. Maybe it could be a still pond. All right. The dog swims at 5 meters per second, but runs at 13 meters per second. Now, if you've never seen a problem like this, you might have to run an experiment, but you definitely have seen these in the homework. If he goes straight there in the water, there's a problem with that. That's kind of like an end point of the problem. But the problem with that is that he can run a lot faster than he can swim. So that's probably not going to be the answer. It would be an end point we might need to check as part of our decision making, so that now the question presents itself. The dog needs to run this way for a bit. At some point he should go over. Now if he goes all the way, he'll have kind of gone way too far. And so to me the question becomes, how far should he run along the beach before he jumps in? Dogs seem to be pretty good at this. So I'm going to label that. I don't know what I should label it. X, Y, it doesn't matter. Let's label it X. And honestly, at that point, you could label this too. If you can label it using the same label, I would do it. Meaning don't label it Y when you can label it 20 minus X. You could label this Y or Z if you wanted. This you know is 13. I think I've run out of things to label. Okay. So what I need is the distance the dog is going to go. I'm trying to fill in time. Again, this is my guiding principle for the whole problem. So how far is the dog going to run along the beach? X. How far, and we're going to divide that by how fast it runs along the beach, which is 13 meters per second. Plus, how far is he going to be in the water? Y. How fast is he going in the water? 5. That's it. There's the whole question. Now we need to somehow turn that into a one variable function. So what can we do? Is there any equation we can write that has to do with X and Y that will allow us to get rid of one of these variables? You can see how the problem tells me what to do, having written this down. I need to get some relationship between X and Y. And I see there's a triangle there. Probably something else I could say too, but I see this triangle. And this may not be an again, I haven't prepared. I haven't tried to come up with the most clever solution. The moment I see this, I'm like, it probably would have been easier if I'd have labeled that X. Too late, I already did it. Okay, so we're going to do 13 squared plus 20 minus X squared equals Y squared. And so I could solve for X or Y. Since I already have kind of Y somewhat by itself, I'm going to solve for Y. Now you might say, what about the plus or minus? Now in this case, I know Y is a positive number because it's an applied problem, and so I've got it. I have a function for time. It's going to be 1 over 13 times X. I'm just doing that because that looks nicer to me. Plus 1 over 5 times Y. Again, apologies if I've typed or written anything wrong here. I guess I'm not typing. The next step will be to take the derivative. We should know how to take that derivative and set it equal to 0 and solve. And it's not going to be quite as bad as it initially looks. So I hope this is sort of helping you. Let's keep going with thought process. I'm going to get rid of that. Let's grab another one. Here we go. And we could easily encounter one here that I'm going to have to think about for a second. That would be great. I'm trying to show you thought process. Let's cheat this time and go right to the end. Find the dimensions that will minimize lateral surface area. Want, minimum, whatever in the world, lateral surface area. Lateral surface area includes the sides. Okay, so we want the minimum surface area. Lateral surface area. So to me that looks like we're talking about 4 triangles. So I want the minimum surface area, and I already am thinking it's going to be 4 times whatever one of these triangle areas is. This looks different to me. I don't remember ever in my life doing a problem quite like this. But I have a plan. Okay, so I know I'm looking for the area of one of the triangles. Okay, now I'm going to go back up. Find the height y and the length of a side of its base x with congruent isosceles triangle sides whose volume is 1/6 cubic meters and whose lateral surface area is as small as possible. So that stuff initially was giving me the dimensions. It was helping me label. So what are they saying? Can we figure this out? We know the volume is this. I think the volume of a pyramid is something in the formulas we give. So right now I am stuck. I'm trying to think of what students had to say, but we know the volume is 1/6, which means I am going to need the formula for that volume. Okay. I think it's 1/3 area times the base times the height. I'm probably going to be wrong. 1/3 area of the base is x squared times the height. Let me pause for a second. Okay, that was it. I had to think about that piece. I wonder if they gave that. I don't know. Anyways, I still don't have this piece. So how am I going to figure out that side length? I see. So I do know a few things. Okay. So I had to, you can see I was kind of stuck. It's helpful because when I'm stuck, I still have a plan for what I'm trying to do. If you view this from the side, I see what their hint was. I can see this little triangle. This must be x over 2. This is the side view. And this must be y. Because of that, I can figure out that length. Is that helpful? Yes. So I can figure out what this length is. Because whatever that length is, you're going to have y squared. And apologies, I should have prepared a little more. But maybe it's good that I'm stumbling a little bit here. So that side is the square root of y squared. And there might be a problem with it. I think there is a problem in the homework that has to do with a pyramid. So you would have some preparation for that. That's that length. That's still not what I want. I want the area of that triangle. Oh, that is what I want. How do you give the area of a triangle? It's 1/2 base, which is x, times height. And height is that length. This is the height of this triangle. I see now. Square root y squared. It's good they gave me that hint, or I wouldn't have made it. Okay. But it's still a 2-variable problem. I don't know why I wrote this. This should have been y. Okay, so we can solve for y. Multiply with, so you're going to get 1/2 1 over x squared. Substitute. Take the derivative. We got it. But I hope you're seeing it's very helpful to identify what it is you're optimizing. Let's try again. Here's another one. What are we optimizing? volume. You can see now you can kind of skip right to it. Volume of a cone. What is the maximum volume of a cone you can make? So what we want, oh, and they even told us the formula. We want maximum volume, and we know volume is this. And we know our overarching goal is to make that a one variable function. What is the maximum volume you can make? Okay, so now I'm going to read the question. You have a circular sheet of paper measuring 6 inches in diameter. Okay, so the radius is 3. Nice of them to give us a picture. From it, you want to make, you want to make a dipping cup. You want to cut out 2 pieces, probably tape it together. Got it. And you want this to be as big as possible. So now let's think about what we're given. And we know the goal. The goal is to make this a one variable function. Again, this is our guiding principle here. So what can I do? What can I say about this? Is there some relationship between R and H that will allow me to get rid of one of my variables? Ooh, that picture was very nice of them to provide for me. R squared plus H squared is 9. Does that allow me to get rid of one of my variables? It does. Here's one where, because this is an R squared, it actually gives a huge hint, which is it might be easier to solve for this and replace R squared. So then you get V equals, now we're going to have a function of H, 1/3 pi 9 minus H squared times H. We're going to expand it all out, take the derivative, set it equals 0, make appropriate conclusions. All right. Let's see another one. That's why I say whatever we're optimizing is my guiding light. It tells me how to do the whole problem. Find the dimensions of the rectangle of maximum perimeter. What do we want? Max perimeter. Now I need to read on. Is it talking about perimeter of the ellipse or perimeter of, the rectangle? Okay. So there's a thing here I want. Maybe just for now I'm going to label this H for the height and W for the width. So what I see is the perimeter is 2 times H plus 2 times W. But I want it to be a one variable problem. Now what do they give me? They give me that these corners are touching the ellipse. Now that might confuse people. That does require, it typically helps to have seen such a thing. But now you've seen it and you'll know this. What do X and Y mean in a function? I'm surprised. This is something that I've noticed over the years. Sometimes people don't know what it means. If I say you're standing on a function, I've even seen problems where I give students the equation of a line and I tell them that this is 10 and I ask them where that dot is. And a lot of students won't know that it's 21. Because that's what the graph of a curve means. The X and Y are from this equation and the X and Y are measured from the origin. So the reason I say that is, if I were to label this X and Y, what can I say about X and Y? Well, that's X, and that's Y. And they're telling me that this is true about X and Y. So anyways, I would have noticed that first. I wanted to talk through it, but I really would have written this, that this is, since H is 2 times Y, I would have written 4Y plus 4X. That's what I would have done right away. But that's because I knew the information they gave me. I was cheating and looking ahead. What are we given? Oh, we're given that thing. So I'm going to solve for either X or Y. It doesn't matter. So how about Y squared over 225 is 1 minus X squared over 400. So Y squared is 225 times 1 minus X squared over 400. So Y is the square root of that mess. Square root of 225 I think is 25, but I'll just leave it here. this goes here. Take the derivative, set it equal to 0, and we'll have our answer. Let's keep going. A lump of clay has a volume of 1,000. It's used to make a cube in a sphere. Find the dimensions of the cube and the sphere that would maximize. That would give the maximum and the minimum surface areas. Okay, so that means we're going to have to make a couple conclusions, but it's not going to change how we do the problem. What do we want? We want to optimize surface area. So what are we going to do? We're going to get a one variable function for surface area. Surface area of what? Find the dimensions of the cube in the sphere that will maximize and minimize total surface area. Total surface area of both. Okay, I need a picture. I need a cube. X, X, X. I need a sphere. I think I would label the radius R. The surface area then would be the surface area of the cube, which there's 6 sides. Each one has area x squared. 1, 2, you know that from a dice. The surface area of the sphere, 4 pi r squared. A cool thing about the sphere is if you take the derivative of the volume formula, you get the surface area formula. That's a story for another day. Anyways, now I know what I need to do. I need to make the surface area a one variable function. So now I need to think about what I was given. What are my constraints? The total volume is 1,000. What's the total volume? X squared plus 4/3 pi r cubed is 1,000. So what do I need to do? I need to solve for either x squared or r and substitute. I think it would be easier to solve for x squared because they match up. So you'd have x squared is 1,000 minus 4/3 pi r cubed. So the reason I solved for x squared is because I saw that that will substitute directly. That'll give me a one variable function. Take the derivative. I'm off to the races. Okay, I feel like that's enough to give you the thought process. Yes, you should also work details, but I hope I've made the case that there's no reason to not be able to start and write a lot of stuff on these problems. All right, let me know if that helps.